Now, another aspect of the Michael reaction that your book really doesn't go into, and I really like to thank Reddit for pointing this one out, is the decarboxylation reaction. So this comes about as a special case of the Michael reaction, specifically when your Michael reagent here is propanedioic acid. So we have propane backbone, and both ends are carboxylic acids. And we react this with an alpha beta unsaturated ketone or aldehyde. Now, to keep it simple, we're not worried with a big complicated unconjugated ketone, but rather we're going to stick to this simple one here. Now, it'll work for any case, just we're going to keep it simple. Now, to keep in mind, to do the Michael reagent, we need a carbene, and to do this, typically what we do for compounds that look like this is we add a strong base, but we've got 2 carboxylic acids here. So it's going to take a lot of base to pull off this hydrogen. So when we run this reaction, we don't run it as is, we run it underneath very basic conditions to pull out the OHs. And what we end up with is actually something that looks like this. We deprotonate 2 carboxylic acids to get the dicarboxylate ions, and then we get the carbene. And the carbene here is going to attack our alpha beta unsaturated ketone, and we're going to get what we expect. So okay, so far so good. You just tag that on to the end, and we've got the carbene, and we're going to follow this up with, second step, an acid workup. So we end up recovering this compound. So why does this video say the decarboxylation reaction? Well, this is the special case when you have 2 carboxylic acids that are geminal. They're attached to the same carbon with the Michael reaction. What will happen is that as we begin to heat this material, and actually we don't need to heat that much, we just got to do it at room temperature, we will end up breaking this bond. And, oops, sorry, I drew it wrong. So carboxylic acid, right, loses its hydrogen. The oxygen will form a double bond with a carbon beside it, and then lose the bond between the carbon, between the 2 oxygens, and the carbon that was the nucleophile in the Michael reagent. So this is going to decompose into CO2 plus H plus that came off the carboxylic acid. 2. And the lone pair that gets left here, I forget the feeling I drew it wrong. Oh, because I did. Sorry. That's what happens when you don't write it out in advance. That carbene that we form by breaking the bond between these 2 carbons immediately picks back up the H plus, and we end up losing that to get CO2 evolution. So this is your decarboxylation reaction. We lose the carboxylic acid and produce CO2. What's driving this? Well, 2 things. First of all, we have 2 carboxylic acids that are geminal. They are pulling a lot of electron density off that carbon, more so than the carbon's actually really able to take. So part of what drives this is trying to get the actual charge on that carbon back up. The second is entropy. When we produce CO2, we actually end up increasing entropy. We end up creating a gas phase. Now, we need to lose this H plus in order to make this reaction happen, but these are geminal carboxylic acids. They're going to be super acidic because on their own carboxylic acids are acidic, bound to the same carbons. They're even more acidic because there's no electron density there. So this is kind of like a self-catalyzed reaction or self-initiating reaction. Once the hydrogen comes off, that lone pair is available to back bond to the carbonyl carbon, which will end up creating a carbene. We lose that hydrogen, which is immediately recaptured by the carbene that's formed. So this is the second, and this is a special case for the Michael reaction, the decarboxylation reaction using propanedioic acid.